What we're going to do in this lecture is look at a topic called spectral analysis and its use in computer science. Now, in this particular lecture, I'm only going to concentrate on the techniques and supporting methods. I'm not going to talk about applications of spectral analysis. That is going to be the topic of the next lecture in this module. But before I do that, I'm going to introduce something. I'd like to introduce the crassest Latin tag ever. This is actually relevant to what we are going to be looking at over the next couple of lectures. So when I was still at secondary school, 45 odd years ago, one of the subjects I studied was Latin because it was still a requirement for university entry in those days. And one of the works we were force fed was a epic poem called the Aeneid by a Roman poet called Virgil. Uh, the Aeneid tells the story of a particular hapless individual called Aeneas, who was a survivor of the siege of Troy, and it recounts how he and his led his gormless followers from one disaster to another before eventually founding the city of Rome. Uh, After one particular disaster early on, Aeneas surveys the followers camped on a beach and tries to console them by quoting this particular line. For sanitae meminisse juvabit, which is he always felt a particularly stupid line to utter. It means, of course, perhaps one day even this will be good to remember. Uh, the poet Virgil is said when he got up in the morning to have written 10 lines of a poem, and he spent the rest of the day discarding 9 of them. So he was left with just a single line. And one has to wonder that if Forza Netaikul Meminisi Juvabit was the survivor, just how bad the other 9 lines were on that particular day. Let's move on to spectral analysis. Perhaps one day even this will be good to remember. So, as an overview, what are we going to be doing in this lecture? I'm going to start off by recounting what spectral analysis actually concerns. And spectral analysis, that's the name given to the study of what are called the eigenvalues and eigenvectors of matrices. It has been adapted to yield a number of very important benefits and has a number of significant gains in computer science. So this includes things such as ranking problems. One has a set of items one wishes to order by some notion of importance. Spectral methods are used to deal with that type of problem. It's been used in image compression and the analysis of large data sets. It's been used in a subject called algorithmic graph theory, which is one of the methods that underpins the study of how social networks evolve. So things such as LinkedIn, things such as Facebook. It is a subject that you are going to see a lot of over the next 2 to 3 years of the degree program. So topics such as data analysis, these feature in a year 2 module. In specialist data science module, but also in aspects of the advanced artificial intelligence module in underpinning machine learning. Algorithmic graph theory, we have a specialist course looking at the evolution of social networks, which is taught by Dr. Zito. That's in year 3. Spectral methods are also important in the subject of computational game theory, which is another final year option. So this is one topic that you're going to meet an awful lot of over the remainder of the degree program. So what am I going to do in this lecture? I'm going to give a brief recap of the key elements which you need to be aware of concerning spectral analysis. I'll give an example of a kind of typical sort of question that you might see, and we'll give usual arrangements for some interaction and questions concerning the material. As I said, I'm going to look at applications of spectral methods in the next tutorial lecture that I give. So in this lecture, we're going to concentrate on techniques. So what are spectral methods? Spectral analysis arises by looking at the consequences of what is called the eigenvalue problem. What's the eigenvalue problem? This is the problem of, given some matrix, you are looking for constant values, and these could be complex numbers, and vectors associated with those complex numbers, associated with those constants, and these have to have the property that when we multiply our matrix by the vector we've identified, that turns out to be exactly the same as multiplying the vector by the constant value that we found. So in other words, the eigenvalue problem reduces the problem of multiplying a matrix by a vector to multiplying that same vector by a given constant value. These constants, these are referred to as the eigenvalues of our matrix, and the vectors, these are called the eigenvectors of the matrix with respect to the given constant that is being used. Every n by n matrix has exactly n eigenvalues. And the reason for that is that eigenvalues arise as the roots of a particular polynomial expression of degree n, which is defined from the matrix. That particular polynomial is called the characteristic polynomial of the matrix. So, what about computational methods? Uh, as regards what is happening in this module, the only one you really need to know about in the short term is something that's called the power method with scaling. There are a huge number of online calculators available which, given a matrix's input, will report its eigenvalues and representative eigenvectors for that matrix. Perfectly okay to use those if needed. So I've given a link to the one at MathPortal on the slide. Extracting eigenvalues and representative eigenvectors, there are packages provided for that in both Python within the NumPy environment and also in Java within this setup called JAMA. So if you're implementing some algorithmic solution which involves the calculation of eigenvalues and eigenvectors for a given matrix, it's perfectly okay to use things like this if you're implementing in Python, things like this if you're implementing in Java. You don't need to duplicate what's already been implemented by somebody else. So what's this power method with scaling? It's quite a straightforward technique, which is actually surprisingly effective under the right conditions. So to start off with, we have our input matrix A, and we're looking for an eigenvector of this particular matrix. So the first thing we do is we take a guess at what that eigenvector is going to be. And a very common choice of that initial guess is just the vector which consists entirely of ones. We form our next guess by multiplying the matrix we're using with with our most recent guess. So we form our next choice by multiplying our vector by our current choice. We then go on to the next value of k, and we repeat that process as long as we want, up to some limit. So we're just, in effect, going round in a loop from here to here to here, and then back again. Sorry, from here to here, and then back again until we're satisfied with the outcome. One of the problems with that basic approach is fairly quickly we end up with quite large numbers. The components of this vector can slow the computation down because they're quite big. And so there's this technique that's used called scaling. And what we do there is instead of we add this an additional step. And what that consists of is we take each component of the vector we've just generated and divide that component by the largest absolute value in that vector. And another condition which may allow us to terminate, we don't need to go up to some maximum value. We might decide to finish if two vectors we've generated in succession look identical or look near enough to each other. So here's an example sort of question. You may be asked to report the eigenvector that's found after a couple of iterations of the power method with scaling on a given matrix. So it could be a matrix like this one here. So if we're doing that, what happens? How do we go about solving that problem? Here's our initial matrix again. We find our first approximation, so we multiply this matrix by the vector of all ones, and we get as an outcome this 4 vector. We want to scale that, so we find the largest component in that vector, that's 7, and we divide each of the components in our 4 vector by the number 7, and we get as an outcome the vector 1, 3 over 7, 5 over 7, 3 over 7. And we go on to the next stage. We find our second approximation by multiplying this matrix by the vector we've just found, carrying out this computation, and we get this as the outcome. We then scale again, find the largest component in that vector, which turns out to be the first component. We divide each component in this vector by that largest value, so that's equivalent to this scalar multiplication here, and we get this as the outcome. A few comments about that. Here's our matrix we started with. If we continued for one further step, this would be the outcome we get. And what we find is that even though we've only taken 3 iterations to reach this, this is already quite a good approximation. If we look at the outcome using standard calculator, then that reports this 4 vector here. Now, this outcome, this approximation, this is already correct to 1 decimal place. We have 1, 0.4, 0.9, 0.4, 1, 0.4, 0.9, 0.4. So it's quite a powerful technique. What about eigenvalues? So this gives a method for computing eigenvectors under suitable circumstances. If we found, even though it's just an approximation, if we found some eigenvector, then we can compute the associated eigenvalue for that vector by finding something that's called the Rayleigh coefficient. And all that involves is we multiply our matrix by the vector we found, and we form the dot product of the result with the vector we found. And we divide that quantity by the dot product of the approximating vector with itself. The dot product, recall, this is a scalar value. It's not another vector. So for the dot product, what we are doing is we are just adding up over all of the components of the two vectors the result of multiplying each component of one vector with the corresponding component of the other vector. And if we apply that to our example, what do we get? Here's what we identified as our approximate eigenvector. If we multiply that approximation by the matrix we started with, then we get this as the outcome. If we take the dot product, the scalar product of this vector with our approximation, then we get this value, 9.76. If we compute the dot product of that vector with itself, we get the outcome 2.06. So the final stage, we have to divide this quantity by this quantity, and what we get as a result is about value 4 3/4. Now that is actually fairly close to a real dominant eigenvalue. Remember this particular approximation, this is resulting after only 3 iterations. If we went on to do 10 or 20 iterations, we would actually have something that was very close to the real dominant eigenvalue. So just to summarize, typical questions you're going to see will really only involve using these basic approximation style techniques such as the power method with scaling and the Rayleigh coefficient. There are a number of more advanced approaches around. You do not need to know how to apply those, but you should be aware that there are such methods in existence. In general, we will not have examples which involve complex eigenvalues, so you don't really need to worry about those. So, as I said, in the next lecture, we are going to move on to look at the reasons why we are studying spectral analysis in the computer science course, and that reason concerns the applications to which spectral analysis has been adopted.